Welcome to the hands-on chapter of our Battery MI series. This is where theory meets practice. Over the next hour, we'll work through 30 code examples covering the complete MI pipeline for battery materials. You'll learn to acquire and pre-process data, build prediction models, forecast degradation, and optimize materials using Python's powerful data science ecosystem. By the end of this chapter, you'll be able to do 4 things. First, build and simulate battery models using PyBA-MM, the leading Python battery modeling library. Second, implement and evaluate capacity and voltage prediction models using random forest, XGBoost, and neural networks. Third, predict cycle degradation using LSTM recurrent neural networks. Fourth, explore optimal materials efficiently using Bayesian optimization. Let's start coding. Before we begin, ensure your environment is properly configured. We need Python 3.9 or higher. Install the required packages using pip, PyBAM for battery simulation, NumPy and Pandas for data handling, scikit-learn for machine learning, TensorFlow for deep learning, scikit-optimize for Bayesian optimization, and Matplotlib with Seaborn for visualization. I recommend creating a virtual environment to avoid conflicts with other projects. The foundation of any MI project is quality data. In this section, we'll cover 7 examples that take you from raw data acquisition through preprocessing, ready for machine learning. We'll work with the materials project database, visualize electrochemical data, and prepare features for modeling. The materials project provides programmatic access to over 140,000 computed materials. Using PyMachin's MP Restor, we query for lithium-containing oxides with cobalt, nickel, or manganese. The query returns material ID, formula, energy per atom, band gap, and formation energy. With just a few lines of code, we retrieve hundreds of potential cathode materials. You'll need to register for a free API key at materials-project.org. Charge-discharge curves are the fingerprint of battery behavior. This example shows how to load and visualize cycling data. The charge curve in red shows voltage rising as lithium is extracted, while the discharge curve in blue shows voltage falling during lithium insertion. The hysteresis between them reflects internal resistance and thermodynamic losses. Understanding these curves is essential for interpreting battery performance. Energy density determines how much energy a battery stores per unit mass. We calculate it by integrating the voltage curve with respect to capacity. Using SciPy's cumulative trapezoid integration, we find the average discharge voltage, then multiply by capacity to get the specific energy of the active material in watt-hours per kilogram. Be careful with this number. It counts only the cathode material, so a real cell, which also carries the anode, electrolyte, separator, current collectors, and casing, lands at roughly a third of it. This fundamental calculation connects electrochemical measurements to practical performance metrics. Coulombic efficiency measures how much charge extracted during discharge relative to charge put in during charging. Ideally, this is 100%, but side reactions like say formation reduce it. Low values warrant investigation for parasitic reactions. Our function calculates CE and provides diagnostic messages. High CE indicates excellent reversibility essential for long cycle life. MapMiner automates the calculation of material descriptors. Using the Magpie preset, we generate over 130 features from composition alone, average properties, variances, element fractions, and more. The code takes cathode compositions like LiCo02, NCA, and LFP, and returns a feature matrix ready for machine learning. This eliminates manual descriptor engineering and ensures consistent feature extraction. Real-world data contains outliers that can corrupt model training. We use z-score to detect values more than 3 standard deviations from the mean. In this example, we identify capacity measurements far beyond any physically plausible value for a layered oxide cathode, which marks them as measurement errors rather than genuinely high-capacity materials. Removing these improves model robustness. Always inspect your outliers before automatic removal, as they might indicate interesting phenomena. Proper data splitting is critical for honest model evaluation. We reserve 20% of data for testing, ensuring the model is evaluated on samples it hasn't seen during training. Standard Scaler normalizes features to zero mean and unit variance, which improves convergence for many algorithms. Note that we fit the scaler only on training data and transform both sets, avoiding data leakage from test samples. Now we build models to predict battery properties from material descriptors. We'll implement 4 approaches of increasing sophistication: random forest for interpretability, XGBoost for accuracy, neural networks for flexibility, and graph neural networks for direct crystal structure input. Each has its strengths for different scenarios. Random forest combines many decision trees for robust predictions. We configure 100 trees with maximum depth of 10 to balance complexity and generalization. After training, we evaluate on both training and test sets. The model achieves excellent predictions with low error margins. Random forest also provides feature importance rankings, helping us understand which descriptors drive capacity. XGBoost typically achieves the highest accuracy among gradient boosting methods. We configure 200 estimators with a low learning rate for careful optimization. The resulting model predicts voltage with high accuracy. XGBoost's built-in regularization prevents overfitting, and its feature importance helps identify the descriptors most relevant for voltage prediction. Deep learning offers high expressiveness for complex relationships. Our network has 3 hidden layers with decreasing neuron counts, each followed by dropout to prevent overfitting. The Atom Optimizer trains the network over 100 epochs. We monitor training history to detect overfitting if validation loss diverges from training loss. The final model achieves competitive accuracy with the flexibility to model nonlinear interactions. Graph neural networks represent a paradigm shift in materials prediction. Instead of engineered descriptors, GNNs work directly on crystal structures represented as graphs. Atoms become nodes with features like atomic number and electronegativity. Bonds become edges with features like distance and bond type. Graph convolution layers aggregate information across the structure, and global pooling creates a fixed-size representation for property prediction. The key advantage: no descriptor engineering required. What if you have limited data for a new battery chemistry? Transfer learning helps. We first pre-train on a large dataset of lithium-ion cathodes, learning general material property relationships. Then, we freeze the early layers and fine-tune only the final layer on our small target dataset of all solid-state materials. This typically improves accuracy significantly compared to training from scratch. Transfer learning is essential for data-scarce applications. SHAP, or S-Hapley additive explanations, provides principled feature importance analysis. Unlike simple importance scores, SHAP shows how each feature contributes to each prediction. The summary plot displays features ranked by importance, with colors indicating whether high values increase, red, or decrease, blue capacity. This interpretability helps validate that the model learns physically meaningful relationships. A single train test split might give misleadingly optimistic or pessimistic results depending on the random split. 5-fold cross-validation provides a more reliable estimate. We train 5 models, each using a different 20% for validation. The mean and standard deviation of error across folds indicate both accuracy and stability. Large variation across folds suggests the model is sensitive to which samples are in training versus validation. The parity plot is the standard visualization for regression model quality. Each point represents one sample, with actual capacity on the x-axis and predicted capacity on the y-axis. Perfect predictions fall on the red diagonal line. Points clustering tightly around this line indicate accurate predictions. Systematic deviations reveal model biases, such as underpredicting high-capacity materials. Always inspect parity plots alongside numerical metrics. Predicting how batteries degrade over time is crucial for lifetime estimation and early failure detection. In this section, we'll implement time series methods using LSTM and GRU neural networks. These recurrent architectures excel at learning patterns in sequential data like cycling experiments. First, let's generate realistic cycle data for training. We model capacity fade as an exponential decay plus random noise, starting at 200 milliamp-hours per gram and declining over 500 cycles. State of health as a percentage shows the same trend, with the critical 80% threshold marking end of life. In practice, you'd load real cycling data from battery data genome or your own experiments. Long short-term memory networks learn patterns in sequences. We prepare data using a sliding window approach. Sequences of 50 consecutive capacity measurements predict the next value. The model stacks two LSTM layers, the first returning sequences to feed the second, followed by dense layers for the final prediction. Training on 80% of data, the model achieves excellent accuracy on test data. Gated recurrent units offer a simpler architecture with fewer parameters than LSTM. Our GRU model uses the same configuration, but trains faster due to its simplified gate structure. Despite fewer parameters, GRU often matches LSTM accuracy for battery degradation prediction. When data is limited, the smaller model may generalize better. Choose between LSTM and GRU based on empirical testing with your specific data. Remaining useful life prediction answers the practical question: how many more cycles until this battery reaches 80% capacity? Using only the first 100 cycles, we fit a linear trend to estimate degradation rate, then extrapolate to the threshold. In our example, the cell actually reaches 80% at cycle 500, so 400 cycles of life remain at the moment of prediction, and the model estimates that to within about 6%. This enables early quality control decisions in manufacturing and accurate warranty predictions. Degradation isn't constant over battery life. Our moving window analysis tracks how degradation rate evolves across cycles. Early cycles often show high fade due to say formation, followed by a stable period, then potential acceleration as cathode degradation mechanisms kick in. Monitoring rate changes helps detect when a battery enters a dangerous acceleration phase, signaling intervention or replacement. Anomaly detection identifies cycles that deviate from normal behavior, potentially indicating manufacturing defects or imminent failure. Isolation forest learns the boundary of normal data and flags outliers. With a small contamination setting, we identify anomalous cycles that warrant investigation. This technique enables early warning systems in battery management systems before catastrophic failures occur. State of health provides a simple battery condition assessment. Our function maps capacity retention to status categories: excellent at high retention, good down to 80%, degradation in progress below 80%, and replacement needed at very low retention. Tracking SO at regular cycle intervals provides a clear health trajectory. This simple metric is widely used in EV battery management systems. When experiments are expensive, we need smart sampling strategies. Bayesian optimization intelligently selects the next material to test based on both predicted performance and uncertainty. In this section, we'll implement Gaussian process regression and optimization loops that dramatically reduce the experiments needed to find optimal materials. Gaussian processes provide probabilistic predictions with uncertainty estimates. Given just a few observations of Nye ratio versus capacity, the GP learns a smooth function with wider confidence bands where data is sparse. The RBF kernel captures smooth correlations between similar compositions. The uncertainty bands are crucial for deciding where to sample next. High uncertainty regions might contain hidden optima. Scikit-optimize GP minimize implements the full Bayesian optimization loop. We define an objective function simulating capacity measurement given Nye ratio, plus realistic experimental noise. The optimizer queries 20 times, each iteration updating its model and selecting the next promising composition. After just 20 experiments, it efficiently finds the optimal Nye ratio with excellent performance. Real battery design involves trade-offs. Higher nickel content increases capacity but reduces cycle life. We handle this by combining objectives into a weighted sum, here 60% capacity and 40% cycle life. The optimizer finds a composition balancing both goals. You can adjust weights based on application priorities. EVs might favor capacity, while grid storage prioritizes lifetime. Safety constraints must be respected. High nickel cathodes above 85% become thermally unstable. We implement this by returning a large penalty for constraint violations, effectively making unsafe regions unattractive. The optimizer finds the best composition within the safe region. This approach generalizes to any constraint, cost limits, toxicity thresholds, or processing feasibility. When objectives conflict, there's no single best solution, but rather a set of optimal trade-offs called the Pareto front. Each point on the front is optimal in the sense that improving one objective requires sacrificing another. We identify Pareto optimal compositions and visualize them as red stars. Decision makers can then choose along this front based on application priorities rather than arbitrary weighting. PyBA-MM, the Python battery mathematical modeling library, enables physics-based battery simulation. Unlike data-driven models, PyBA-MM solves the electrochemical equations governing lithium transport, reaction kinetics, and charge transfer. This provides interpretable predictions and enables what-if analysis of design changes. Let's see it in action. The Doyle-Fuller-Newman model is the gold standard for lithium-ion battery physics. We create a DFN model, load PyBA-MM validated Chen 2020 parameter set for a graphite versus nickel-manganese-cobalt cell, and simulate a 1C discharge. The result shows voltage dropping from full charge to cutoff over 1 hour. PyBA-MM provides access to internal variables like concentration profiles and reaction rates, enabling deep understanding of battery behavior. Rate capability is critical for fast charging applications. We simulate discharge at various C rates from low to high, showing how capacity and voltage are affected by discharge rate. Higher C rates cause larger overpotentials and earlier voltage cutoff, reducing usable capacity. This analysis helps identify rate-limiting steps: ionic diffusion in electrolyte, solid-state diffusion, or reaction kinetics. Real batteries differ from theoretical parameters due to manufacturing variations. Parameter fitting adjusts model parameters to match experimental data. We minimize mean-squared error between simulated and measured voltage by optimizing electrolyte conductivity. The SciPy minimize scalar function finds the optimal parameter value. This calibrated model then predicts behavior under new operating conditions with improved accuracy. Now it's your turn. The challenge is to design an optimal NCM cathode material using everything we've learned. Start by collecting data from materials project on nickel-cobalt-manganese oxides. Calculate descriptors and build an XG-boost capacity prediction model. Use Bayesian optimization to find the best Nye, Co, Mn ratios while respecting safety constraints. Finally, validate cycle performance using PyBA-MM simulation. Your solution will be evaluated on 4 criteria. Capacity should exceed a high threshold. Cycle life should reach several thousand cycles at 80% retention. For safety, nickel ratio must stay below the thermal stability limit. For cost, minimize cobalt usage. Submit your optimal composition, predicted performance metrics, and the complete Python code. This project integrates all the techniques from this chapter into a realistic material design workflow. Congratulations on completing this intensive hands-on chapter. We covered 30 code examples spanning the complete MI pipeline. data acquisition and preprocessing in examples 1 through 7, capacity and voltage prediction in examples 8 through 15, cycle degradation forecasting in examples 16 through 22, Bayesian optimization in examples 23 through 27, and pi-BA simulation in examples 28 through 30. You now have a practical toolkit for battery MI projects. In Chapter 4, we'll see how these techniques are applied in real industrial settings. You'll work through 5 case studies drawn from published industrial and academic work: solid electrolyte discovery for all-solid-state batteries, sulfur cathode hosts for lithium-sulfur cells, machine learning fast-charging protocols, cobalt-reduced cathodes, and sodium-ion materials. These examples show how MI accelerates product development and improves manufacturing quality at industrial scale. See you in the final chapter.